Okay, 6.3 corollary B part. Let x and y be normal spaces with x finite dimensional. Then every bijective linear map from x to y is a homeomorphism. And in the part A, we already proved that a linear map from a normal space x to a normal space y is a homeomorphism if and only if there are alpha beta greater than 0 such that beta into norm x less than or equal to norm of x less than or equal to alpha into norm x for every x belongs to x. Therefore, to prove a bijective linear map from x to y is a homeomorphism, we can use this result. Moreover, all norms on x are equivalent in this case. That is, if x is finite dimensional, then all norms on x are equivalent. And with each of these norms, x is complete. If the dimension of x is n, then clearly there is a linear homeomorphism from Kn onto x. Idana 6.3b part. Assume that x is finite dimensional. X is finite dimensional and f is a map from x to y. That means f is a linear map from a finite dimensional normal space to y. Then by theorem 6.1, f from x to y is continuous. Theorem 6.1 says that every linear map on a finite dimensional normal space is continuous. വളരെ പെട്ടെന്ന് ഇവിടെ f continuous ആണ്, linear map f continuous ആണ് എന്ന് മനസ്സിലായി. Then ഇനിയും ഈ ഹോമിയോമോർഫിസത്തിന് എന്തൊക്കെയാണ് നമുക്ക് ആവശ്യമായിട്ടുള്ളത്? By the assumption we have the map f from x to y is a bijective linear map. Now f is bijective, and since x is finite dimensional and f from x to y is a bijective linear map, y is also finite dimensional. Because നമുക്കറിയാം 1-1-1-2 മാപ്പിംഗിൽ domain and codomain have same cardinality. Therefore, y is also finite dimensional, and moreover, if the dimension of x is n, then the dimension of y is also n. And f is bijective implies its inverse exists, and we know that if f is a linear map which is bijective, then its inverse is also linear. Again, then by theorem 6.1, f inverse is a linear map from a finite dimensional normal space y to x. Therefore, f inverse is also continuous. Now, f is a homeomorphism. Next, to prove all norms on x are equivalent. For this, assume that x have two norms, norm and norm prime, where x is a finite dimensional normal space. The norm and norm prime are equivalent or no? To prove norm and norm prime are equivalent, by theorem 5.7, we have norm is equivalent to norm prime if and only if alpha greater than and beta greater than 0 such that beta into norm x less than or equal to norm prime of x less than or equal to alpha into norm x for every x belongs to x. Now the identity map I from x to x defined by I of xx is a linear homeomorphism. Clearly, identity map is a linear homeomorphism because I of x plus y is equal to x plus y and I of kx is equal to kx, that is k into ix. And now I is a linear homeomorphism. Then by part A, we have there exists alpha beta greater than 0 such that beta into norm x less than or equal to norm I of x less than or equal to alpha into norm x for every x belongs to. There is some alpha beta greater than 0 such that beta into norm x less than or equal to norm prime of I of x less than or equal to alpha into norm x. That is, we take here the norm of x as norm prime. Because norm and norm prime are norms on x, we can take norm prime I of x here. Beta into norm x less than or equal to norm prime of I of x less than or equal to alpha into norm x for every x belongs to x. That is, beta into norm x less than or equal to what is no I of x, that is x, norm prime of x less than or equal to alpha into norm x for every x belongs to x. Then by theorem 5.7, we get norm and norm prime are equivalent. Okay. അപ്പോൾ എക്സ് ഫൈനൈറ്റ് ഡയമെൻഷണൽ ആണെങ്കിൽ അതിനുള്ള എല്ലാ നോമുകളും equivalent ആണ്. Finally, if x has dimension n, then we know that there is a bijective linear map f from Kn to x. അത് ഏത് മാപ്പാണ്? അപ്പോൾ x1, x2, etc. xn be a basis of x. Now we can define for any a1, a2, etc. an in Kn, f of a1, a2, etc. an is equal to a1 x1 plus a2 x2 plus etc. plus an xn. Clearly this belongs to some element x in x. അപ്പോൾ ഇവിടെ കൃത്യമായി ഏത് കെയിനിലെ എലമെന്റിനും, അതായത് ഇസ് ഓർഡേർഡ് n ട്രിപ്പിളിനും ഈ ബേസിസുമായിട്ട് ലീനിയർ കോമ്പിനേഷൻ സ്കെയിലേഴ്സ് a1, a2, etc. n എടുക്കുമ്പോൾ അത് എക്സിലുണ്ടാവും. This is a bijective linear map clearly. Now if x has a dimension n, then there is a bijective linear map f from Kn to x. Then by the above result, f is a homeomorphism. What about the completeness? Again by a part. There is a linear homeomorphism from x1 to y, then x is complete if and only if y is complete. And we know that Kn is complete in any of the norms, norm p, 1 less than or equal to p less than or equal to infinity. Therefore, this x is also complete in every